right, here we are to do the second installment on this section, graphing polynomial functions. I'm just going to use this as a reinforcement for what we did before. There's not going to be a lot of new information here, but we're going to practice a couple story problems to kind of help you use your calculator and figure out how to do these and to try to interpret the problems. We're going to tackle problems 31 through 35, and this is from your homework, so you might want to get your book out and follow along with me. That's on page 357. We're going to start with problem number 31 and 32. All right, let's go take a look at it. All right, once again, I'm on page 357. Let's take a look at problems 31 and 32. We need to kind of think this through a little bit, see what's going on. This is called child development, and I like the fact that they're discussing this here, because a lot of times kids tend to compare themselves to one another, and you know, kids are so different, and they just doesn't matter, just it's in their genetics when they are developing at a certain times, and that means not just physically, but that means you know, intellectually too, when they're ready for something, like when they're ready for algebra. It varies a lot. So student says, well, I didn't take algebra in the 8th grade. Well, you know, everybody's different. Some are ready in the 8th grade, some are ready in the 9th grade, maybe there's a couple ready in the 7th grade. So child development is a good topic for us to talk about. Let's take a look at it. For exercises 31 and 32, use the following information. The average height in inches for boys ages 1 to 20 can be modeled by this equation. And there it is. You can see that equation. You'll notice it says b of x. B stands for boys, obviously. And before we get too deep into this, let's just think about this picture in just a minute. If you take a look at this first number, it's x to the 4th. That's an even polynomial. And so it should enter and exit in the same hemisphere. And it's negative, meaning it's going to open down, not open up. It's going to open down. Okay? So we can kind of see that from the picture. However, what we're interested in is this graph between ages 1 and 20, or I guess we could make it from 0 to 20, from birth to 20. And then it goes on to say, where x is the age in years, okay? Then there's another equation. The average height for girls ages 1 to 20 is modeled by a different equation, g of x. Of course, g here stands for girls. And this equation also is a negative x to the 4th equation. So these two equations are both similar. Now, we may not see a whole lot of this graph because we're only looking from age 1 to 20. But let's go ahead and put this on the calculator and see what it gets. 31 says, graph both equations by making a table of values and checking out the domain. We're actually going to just use the calculator. We could make a table of values and plug every one of these numbers in for x. It would be a lot of arithmetic, and in fact, we could use table to do that. But let's go ahead and plug this into the calculator, okay? All right, I've entered both equations in my y equals screen, one for the boys and one for the girls, and I put the boys first here because they were listed first in the book, and then the girls is second here because they were listed second in the book. And in fact, I triple checked my data entry. There is a lot of numbers here and a lot of decimal points and zeros. One of the things that needs to be a good habit for you is to always double or triple check your entries. It's so easy to make a mistake. Now, I could have still made a mistake. We're going to find out when I graph this. But let's say, again, what we're expecting to see. Well, we're expecting to see a polynomial where it opens down. It's even, so it should enter and exit in the southern hemisphere and open down. Now, we're going to go ahead and graph this, and just for the fun of it, I'm just going to graph this using a standard window. So I'm hitting zoom, standard, and let's see what happens here. Okay, well, it looks like we're getting the left side of our of our function, but we're not seeing the top of it. Oh, there's the girls coming in. Okay, and we're not seeing any of this stuff on the right. Remember, we've got to go out to year 20. So if each of these tick marks in standard form is 1, I'm only going up here to 10. So I got to go at least out to 20. So I'm going to change my window, and I've got to go higher too. So I'm going to change the y max to, I don't know, let's go up to, I don't know. It's talking about height. This problem is talking about height in inches. Well, boys and girls, their maximum height's about 6 foot. So just to make it a little bit bigger, let's use 84 inches. That would be 7 foot. That'd be the maximum. And I don't need to go into negative. Oh, I'm sorry. This is x. I should go back and x max is going to go from year 0. So let's just go -2. And we're going to go up to the 20th year. It said in the problem the 20th year. So let's just put 25 in here. And let's make our x scale go by 2s, okay? That'll give me about, 10 tick marks or so. The y minimum, well, their height can't be less than 0. So let's just go down to 0. Actually, I'm going to go a little lower so I can see the x-axis. And their height is going to be maximum about 7 feet, which is about 84 inches. So somebody there might be. Now we're looking at the average height. So the average height is clearly not going to be 7 feet. So we should have enough room here. And let's make us go by a scale of, oh, I don't know, let's go by 6 inches. That way we can go by ½ feet. And that'll give us, every 6 inches. Remember, this is about years on the x-axis and height in inches on the y-axis. So let's graph it. All right, here's the boys coming in here. And it looks like it's turning down like it's supposed to. And here is the girls. And it is coming down like it's supposed to. Now let's talk about the implications of this. We know that people's height does not decrease significantly as they get older. They might get a little shorter. Their vertebrae might be compressed a little bit, or they're not standing up as straight as they get a little bit elderly. But we know that this is not going to go down that much. Well, remember, we're supposed to only be graphing this from year 1, and we'll call it 0 here, from year 0 up to year 20. So I'm going to put a vertical line in here by using the draw feature. Remember how to do that? I'm going to go second draw, and I'm going to put a vertical, whoops, actually let's go back to my quit screen here. I'm going to go second draw, vertical, and I'm going to put a vertical line at year 20. Because I want to see where the end of my domain is going to be. No, it's not giving it to me. Let's go back and do it again. I forgot to hit enter. There we go. Okay, so it looks to me like it's kind of going downhill here for a little bit, but that's probably not terribly accurate. All right, let's see if we can interpret what's going on with the graph here. Now remember, we're talking about age and we're talking about height. Now the red one here that I've got on my graph here is the girls, and it makes sense that at maximum height, girls are typically, not always, but typically, this is the average it says here, typically shorter than boys are. And boys actually continue to grow after the girls have stopped. You'll notice the girls kind of stop growing right in here. What would that year would that be? 2, 4, 6, 8, 10, 12, 14, about year 14 or 15. And we know that's true, that girls typically kind of stop growing vertically about 14 or 15, Boys will continue to grow a little bit longer, maybe into their 18th year or so, 19, maybe even 20. So this makes sense that boys are growing a little bit longer than the girls. And you'll also notice that these lines are almost perfectly parallel through here. There's little spurts left and right, a little bit of spurts that go on. And remember, we're going by 6 inches on, or excuse me, 6 inches on the y-axis. So 6, 12, 18, 24. It says that people are born about 24 inches tall. Well, that's true. Typically, people are born, newborns are about 20 inches long or so. But it's, that's pretty close. So this is a representation of the growth curve of boys and girls, and they're comparing the two because we've graphed them both on the same picture here. So it says in our problem, graph both equations, and we could go into the table here and we could find all of these approximate heights. And if we went into table here, and we could find all the heights, we're not going to go into negatives, let's go down here. So it says that at year 0, when somebody's born, boys are typically 25 and girls are 26. That's a little bit high, and as we get a little bit older, let's go up to year 18 and see what happens here. In year 18, it looks like boys have kind of topped out right there, which is kind of what we figured. Boys kind of topped out in year 18, and girls, I'm sorry. Guys go a little longer than that, don't they? Yeah. Guys is about 19. It looks like it's topping out right here. That number's getting smaller now. Girls look like it tops out around 18 or so. So I was off a little bit. The girls actually looks like it rises until they're about 18. So now remember, these are average numbers. This does not mean everybody. We're just talking about averages. We're talking about mathematics. We're not talking about the real world. And somebody always wants to say, well, what if? They play at the what if game. Well, yeah, we're looking at averages. There's always going to be somebody that's an exception to the rule. There are going to be kids that are shorter and taller because of the genetic situations. But this just kind of gives us a comparison of the two. So we could actually go in here and jot all of these numbers down. The heights are in blue and red here, and the age is over here in the x column, and we could plot all of those points. All right, let's take a look at the second question here for number 32. All right, question 32 says, compare the graphs. What do the graphs suggest about the growth rate for both boys and girls? Well, we've described that already. That boys and girls typically are parallel most of their growing up. It's a little variations here and there. There are some spots, and if we get a more detailed look at our graph, we would see a little bit more. Something else I probably need to mention about this graph. Let's go back and look at the graph again. Okay, now I'm going to zoom in so you get a little bit more detail here. You'll notice that there are minor fluctuations in the graph a little bit. For example, there looks like right here, there's a spurt. The boys spurt about 4 years old, but then that levels off, okay? The boys kind of catch up with the girls. The boys starting behind the girls at birth, and then they kind of catch up a little bit according to this, and then they run parallel a lot. Right about here, notice they start to diverge. One's leaving the other, 2, 4, 6, 8, 10, about 10 or 11 years old, and we start to see that's true. That girls kind of slow down in their growth, and the boys just have growth spurts there. As we understand human development, we understand that everybody develops at a different rate, but there are some patterns that happen. And we know that boys, about year 10, 11, 12, 13, they really are physical. It's hard for them to sit still, and possibly that's because they are growing so much. They need to be out on the play yard, playing soccer and football and doing something physically because there's a growth spurt here. And we also find that they tend to be a little less interested in schoolwork because it could be because of this growth spurt that's happening here. Usually about the middle, kind of the end of elementary school and in middle school, girls tend to do better in school. Maybe it's because there's not so much energy in their body being put into growing physically. So, but the boys tend to level out, and they tend to catch up academic growth too. They don't oftentimes get that interested in school until after they're graduated from high school. So there's a lot you can learn looking at a height curve and speculations that you can make. I'm drawing some conclusions, and they may or may not be valid in all instances, but we are trying to understand this in terms of the averages. All right, let's look at a different word problem. Hopefully you learned something again about how to set this up in terms of the domain and the range, getting the scale right, getting the tick marks on the bottom and on the side, and trying to make some interpretation of the graph. Okay, let's look at another one. All right, let's take a look at problems 33 through 35. Physiology. A little science question, a little medical science question. During a regular respiratory cycle, breathing, the volume of air in liters in human lungs, can be described by this function, V of t. Well, V stands for volume, of course. And t, what is that? Well, it says where t is the time in seconds. Now, as you're breathing in and out, you're expecting the volume in your lungs to increase. The volume of air in your lungs will increase and decrease when you're inhaling and exhaling. And it's given by this function here. Now, you'll notice the way that they wrote the function in the book. The highest degree here is third degree. It's at the end here, so don't mistake this for a linear equation or a quadratic. It's a third degree function, so maybe they should have written it backwards here. But if it's a third degree function, let's think about what we're expecting to have happen. It should enter and exit in different hemispheres, and it's negative, so it should be sloping downhill. It should go down. So I'm expecting a function to kind of go down. But we're going to take a look at the respiratory cycle from time starting at 0, when you're starting a breath, until however long it takes. I don't know, how long does it take to take a full breath? I don't know, maybe 10 seconds or so. So we're going to go ahead and put this in the calculator and see what we got. All right, I've entered this in the calculator, and you see I entered it exactly the way that the book gave it to me, but I could have entered it in any order here as long as the signs in front of the coefficient are kept with that particular term. So we can see again that this is not a linear function. It's not a quadratic, x squared. It's a cubic function. We look at the highest degree, and it's odd and negative. So I'm expecting that the graph should go downhill from left to right. Let's go ahead and take a look at this. Now, these numbers are pretty tiny, but let's see what happens if I just hit zoom standard here and see if I get a good picture of it. Okay. Yeah, it came in from the north and it's leaving in the south. That's what we expect. Okay. And it is a cubic function. Now, we've got way more graph here than we need. Why is that? Because we're talking about taking a breath, and you don't have a negative time here. So we're going to change the window so that we're just looking at breathing from 0 and on. And it looks like here it goes down, dips down below negative. We're not going to have a negative volume in your lungs. We're not talking about pressure, we're talking about volume. There might be negative pressure in your lungs, but there's no negative volume. So we really are only concerned here from 0 to about 5 or 6. So I'm going to change my table. Now you'll notice I'm having to interpret the story problem so that I get my graph so it's manageable. Okay, this graph that's like this doesn't say much. So we need to manage the graph by changing the window. So I'm going to go over there, window. I want my x minimum to be 0, but actually let's make it a little smaller than that so that I can see the y-axis. I got an x max of 10, that's fine, but I don't need that much. Let's just go up to 6. Okay, and let's make the scale go by ones, that's fine. And the y minimum, well, I just need to go down to where the volume is 0. Let's go just a little lower than that. Let's put -2 in again so I can see the x-axis. And my y max, the volume, is going to be 10 liters of air. No, that's way more air than we're going to have in our lungs. How much air do you think's in your lungs? Well, let's put 5 liters in there. Let's see what we get. Let's graph it. Okay. 5 is way more liters than I need. You can see that this goes, 5 liters is up here. We only have, looks like about 1 liter. 1, 2, 3, 4, 5. We only have about 1 liter. So let's change the window so that we have about 2 liters of air. We're going to change this to a y max of 2. And let's change our scale maybe to go by 0.1s. That way it's going by tenths of a liter. Okay, let's graph it. So here we are. Okay, that's better. You know, I don't need all of this at the bottom. So I'm going to change this window at the bottom, window minimum, y minimum. Let's change the y minimum to go down to only, say, -0.5 or so. Graph it again. There we go. Okay. So now what am I concerned about? I'm just concerned about going from 0 to here because we're talking about positive volume of air in your lungs. So the question asks us, estimate the real zeros of the function. Well, it looks like it's crossing the x-axis back here at negative. Well, that doesn't make any sense. We don't really care what's happening in going back in time. What we care about is graphing it from 0 and forward. So it looks like when the time is starting, you have 0 volume in your lungs. Okay? And then you breathe in, and then you breathe out, and when it's 0 volume again, you've had a complete breath. Okay, so if you completely expel every ounce of added air in there, you're now back here. So we're just concerned about these two numbers. And we can go to our table to see where those are. So I'm going to go second table. And I got to go up a little bit here because I got to go back to x is 0. Here we are. Okay. Now as you look at this, you can see that when we start our breath at 0, we have 0 volume in our lungs. And here it's going up, 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 and right about here it starts to come back down until about 6 where it's negative again. So we're only concerned from about 0 to 6 or so. Okay, so we can kind of see that this is making sense here. Let's look at the graph again. Estimate the real zeros. Well, we can actually calculate the zeros here using our zero feature on our calculator. So I'm going to go second calc 0, and I'm going to calculate this one on the left, although I already know it's going to be 0, 0. But let's just make sure. Let's put it over here to the left of the crossing, enter. To the right of the crossing, enter. Enter again. Yeah, in fact, that is 0. All right, let's find the other one, the one on the right over here. So second calc 0. Let's move our cursor just to the left of that crossing, left bound. Right there, hit enter. Now we're going to go to the right of that crossing. There we go, enter. Enter again. And it appears that it's at about 5.3. I'm going to jot that number down on my board here. At 5.30, there is a crossing. And we know there was a crossing at 0, 0. So we've got our two zeros. So in answer to question number 33, estimate the real zeros, we see that there's a crossing at 5.3. So what this is telling us is that when you start your breath, at 0, you breathe in, you've completely gone through one respiratory cycle at about 5.3 seconds. So if you time yourself and see how long it takes you to expel all that air again and start over, it should be about 5.3 seconds. That would be about 12 breaths a minute, and that's about right. People breathe that much. Okay? All right, let's look at problem number 34. It says, about how long does a regular respiratory cycle last? Well, it lasts about 5 seconds. In fact, about 5.3 seconds. How long does a regular respiratory cycle last? About 5.3 seconds. And question 35, estimate the time in seconds from the beginning of the respiratory cycle, from the beginning of this respiratory cycle, for the lungs to fill to their maximum value. Well, where is the maximum volume? Well, it's right here at the top. It's not really a parabola, but it is what we call a relative max. And so we're going to find that relative max, and we're going to do it by going second calc, maximum, and we're going to move the cursor. It's asking for our left bound. Move your cursor to the left of that mountaintop. There it is. Doesn't have to be real close. Enter. Move the cursor now. It's asking for your right bound. Move it to the right side of that mountaintop. That's good enough. Enter. And then enter again. And there it is. It tells us that our max is at about 3.4, 0.97. I'm going to round a little closer there. 0.97. So our max is found at about 3 seconds, 3.4 seconds, right here. And the volume is about 1 liter. About 1 liter. So that tells us that as human beings, we breathe in about a liter of air. Maybe a little less, depends on the person, of course. And it takes about 3.4 seconds. So in answer to the question here, estimate the time, it's about 3.4 seconds. Now we're almost done with this problem and with this video. I'm going to wind this up. But before we do, I want you to take a little note about this graph here. You'll notice that this graph is not symmetrical about that top. What is that telling you about the way people breathe? Do they breathe in the same amount of time they breathe out? No, it appears that we take longer to breathe in, and when we expel air, we breathe it out faster. I know that if anybody's ever done any study on mountain climbing, I've done some, haven't climbed much, but I know that if you want to make sure the capillaries, all the little alveoli or whatever they're called, in your lungs get filled up with oxygen, you breathe out very quickly when you go up in high altitudes, and it forces that air into the cells of your lungs a little faster. You're creating some pressure. And what we're doing here by breathing out faster is we're actually creating a little bit of pressure in our lungs that's pushing that air into those capillaries a little quicker. Okay? So when we breathe in, it takes longer than when we breathe out. Just a little bit of a silent. You can learn a lot from a graph that you can't learn by just looking at an equation. All right, well, those are the problems 31 to 35 on your homework. You got a few more of these to practice. Once again, the key here is being able to get this graph in a way that you understand it. It's not got too much graph showing, and you're only looking at the part that really matters here. We didn't care about the negative time, and we didn't care about the negative volume. You're going to have to learn how to interpret this data so that you can make some sense of these graphs. Let's take a look at your homework now. All right, here are the next two assignments. I'm gonna not cover anything else in this section, but I'm gonna give you 2 assignments to practice. This needs a lot of practice, particularly working with your calculator and getting that window right and figuring out how to find the zeros and the maxes and the mins. So here are the 2 assignments coming up. Friday is 51 and Monday is 52. We got another assignment next week, which is going to tackle the next section of this. make sure you practice this. This is one of the most important skills you're going to get in algebra. In fact, in science, it's one of the most important skills, your ability to take a picture and calculate those magical spots, those important places, you know, the y-intercept, the zeros, the maxes, the relative maxes and the mins. Okay, as you can find those, and they're all in Second Calc menu. So you can find those, then you can make some sense of what everything means looking at that graph. All right, enjoy. Have a good one.